Hello, and in today's STM32 programming, we are going to be covering the basic ADC. So for the ADC, we need to go to our configuration. For this particular STM, we have two ADC peripherals, but they do share the same pins. We are only going to be configuring ADC 1. I'm going to be using 3 ADC pins, so iron 0, iron 1, and iron 2. So then our pins are selected and automatically configured here for us. Our configuration is going to be independent mode. Our scan conversion mode is going to be set to disabled, continuous conversion mode to enabled, so that we continuously have a conversion ready when we want to query the ADC. Then enable regular conversions as enabled. Our number of conversions is going to be 3. This does not really matter when you're doing the basic ADC, but for future, we are going to be using 3 conversion. And then our external trigger is going to be a regular conversion launched by the software, so we need to do a call from the software's end to start a conversion. We have all these other events that we can use to trigger a conversion, but for now we are going to stick to a software launch conversion. Then we have our ranks, and this is going to be which channel does the first conversion and what is the sample time going to be. I'm going to max out the sample time since I'm using a low frequency source, so I don't need extreme sample times, and we do this for the same for all of the others. We just change the channel that we are using on each rank. So this determines the order in which you will have your sampling. So it will first sample 1, then 2, then 3. For the basic ADC, it's not that important. We are going to disable injected conversions and enable the analog watchdog we are going to disable as well. Then I think I missed the data alignment. We are going to be right aligned, so the 12th bit is going to be our most significant bit. And for this particular STM, it has a 12-bit ADC, so you can have a 0 to 4095 as your maximum value. So 4096 steps, and that's pretty much it for the conversions. We can save this and generate our code, and apparently I've forgotten to do a configuration. It's complaining that I haven't configured the clock correctly, so this is the ADC clock. So we say just solve it for us, or apparently it doesn't want to do that. Okay, so a prescaler of 6 is required, so our ADC is going to run at 12 megahertz. And just a note from the datasheet. Our ADC clock, we can determine how long a sample will take depending on the formula given here on this particular ADC. It may be different for other STMs, but usually there is a formula for calculating your conversion times. So if we have a 1.5 conversion time plus 25, plus 12.5 is 14 cycles, so we get a 1 microsecond conversion time. In this case, if we take hours, it will be a 12 megahertz plus, I think it was 256. Let me just double check that. This number. This will give us the number of cycles plus 12. Let me double check that. 12.5 cycles. That will give the conversion time that we require. You can go higher settings if you want less accuracy on your bits, but I'm not going to get into that. So let's save this. Okay, so that generated our project. We're just going to have a look at what it generated in CMain for us. All addition it added was the ADC 1init function. So we're just going to cut that, add it to our main.cpp so that we have it. And then in our project, we delete the main.c. And so let's see, delete again, continue. Okay, then we go to our .h. Since we regenerated our file, we have to go to the whole config and reset our UART registers because we're using the DMA UART from the previous tutorials. We can remove, this is the wrong CPP main. Okay, we're in the correct one now. We can just remove this. Okay, then we double click our main, that we go to our projects again. Now I've copied over all the files from the previous tutorials that we need. So we are going to create a new source file which is going to be ADC underscore hull.h, actually .cpp. And we copy that. Click finish, it'll generate the file for us. We say new header file, and that is going to be our .h file. And we can put our .h file here on the side and close our config and our startup.s. And then we just check if everything builds. Double check. Okay, great stuff. We're building. Then in our .h file, we include ADC underscore h. And we include our main.h, and then we can start creating our class. And this will be our ADC base. And we add our public, protected, and our private sections of the class. Okay, we start with a constructor. And our constructor into our C file, and we need to add our include ADC underscore hull.h. And now we can go look at our main.h, which contains nothing of use. Go look at our ADC.h, and there is our handle. So we're going to have our handle, and we're just going to call that ADC that.h, and we're going to make that protected as our local storage for that pointer. And then we look at our ADC type def, so it's this function, and then we need the instance out of that def. So we add that, and we add our instance, and we make our class variable private and underscore instance. So that's our two variables that we require. Then we create a hash define, and we say ADC underscore count, just like we did with the UART. Then we say create a private static bool, and that is going to be is underscore init. That is going to be an array of ADC count. So this will keep track of which peripherals are initialized. And we're going to add another hash include. And this is going to be actually a standard library, vector. So our standard vector library from C++. And then we are going to create a std vector. Type is still unknown. And then we'll say channels. I'll figure out what the type is in a bit. Okay, then we go back to our ADC hull. We copy over our variables, and then we construct our two variables. So ADC h is constructed with our input handle, and our instance is constructed with instance input. And then in here we are going to have to initialize our ADC. So that's going to be a private function of void init. That's going to be void as well. Just move this in. Then we add void init and void. We add our ADC base in front. And now we need to initialize our ADC. And we say if the underscore instance is equivalent to ADC1, I believe. Let me just double check that. Open declaration. So this is in our STM32F103 file where we define the registers. So this is the ADC base register. So this is going to be ADC1, which is correct. So if the instance is equivalent to ADC base, we say if our ADC init of the 0th index is already correct, then we say return, because we are already initialized. And we say is init equals true if it's not initialized already. And then that function we grabbed earlier, this one, we take that, remove the comment, we go back to our ADC hull.cpp, and then we just call the initialize function for ADC1. Let's see what ADC1 does. So it initializes, it creates a S configuration and initializes the whole structure to 0. Then it initializes our ADC1 variable to the correct values and all our configuration. Then we have our whole init. If it fails, we error handle, and then we start setting up our channels. So we can see here sconfig channel equals 0, and then it sets the rank of the ADC, and then ADC sample time is 239 cycles, and then they have the 0.5 as the underscore at the end. And then it just continues setting up channels. Our MSP init just sets up the pins for the analog conversion. Let's just see, that is called here somewhere. Doesn't look like it. And then the deinitializers just switches off the ADC. So that is our init function. Then we just call in our constructor init. As easy as that. We're just quickly gonna go back in here because I need to know what the channels type is. Okay, so it's ADC channel con type def. So our vector is going to be of that type so that we store the channel configurations. We go back to our hole and we are going to create the destructor, and that's going to be of type void. And we give it the namespace, and then we take channels, and then when we destruct, we just clear the vectors. Okay, and now we need to add a reference to our static array here, and that's going to be, just copy this. And we say our entire brace is false. So the entire array is false. And then we just tell it which class this belongs to. So that's our static variable. Just quickly build, see what happens. No errors. So now what we're going to create is a function that adds channels to the ADC. So we say void add channel. And that's going to take in a uint32 underscore t, which is going to be the channel, and then a uint32 underscore t, and that is going to be the sample time for that particular channel. And then we implement the function, add it here. Okay, now we need to figure out what we can pass in here. We look in our project, we see ADCH is not very useful. So we go to the init function, see if we can find something useful in there. We can see here's the ADC channels. You can see that's a uint32. So channels 1 and 2 is what we care about. So this is already defined. And then we have the sample time values, which is also defined for us over here, as well as the ranking of the ADC. So that is what we are going to be passing in, and we can also see that everything is uint32s. You can calculate the value for yourself, but this is just a lot easier to use the whole underscore.h file. Then we need to create a ADC channel config def in here as a temporary variable. We just called it sconfig. And if you're wondering why I'm picking sconfig, we go to the init function. And you can see it's defined here as sconfig. So actually we can just copy this from the init function. So we are overriding what the default init function is doing. Like our sconfig, and instead of channel 0, we say the channel. And then the sample time is going to be the sample time. And it's always going to be rank 1 in here. And then we take our channels vector. And we say push back. Then we're going to shrink the vector, since vectors allocate unnecessary extra data. We don't plan on changing the size of the vector that often, so it's not a massive penalty to do this. Shrink to fit. So that will shrink the vector to its minimum size, so the actual true size that you call. And what we're going to add to the end of the vector is the sconfig. So now we have a method of tracking which channel we are using. And now that we have a method to add channels, we need a method to translate the channels. So we create a private function, and that is going to be of type all status def. So that's what it's going to be returning. And that's going to be set underscore channel. And that takes away the whole thing. We call it set channel. And what we're going to pass in here is a uint8 underscore t, and it's going to be a channel as well. And I need to correct that data type. And we just copy that. And we say set channel. And we say if our channels, actually our input channel is greater or equals to our vector of channels dot size, we return hull underscore error. Otherwise, let me go look at our ADC init again. Then we see our ADC hull config, and we can have a look at that. Configures the selected channel to be linked to the regular group. This will set the ADC conversion of that particular channel. So then we need to configure the channel. We can take, this takes in a parameter of what? Let me just double check that again. The hull and then the sconfig. So first going to take our ADC handle, and then the next thing it's going to take is our channel. Let me just fix that spelling. That's going to be our channel, and we need to pass it in as a reference since this is a hard set value. Let's just see if this returns anything. All status def. Okay, so we can just return this. So now we have a method of adding channels to our ADC. We have a method to set the channel that we are going to use for the ADC. And now we need a method to read the ADC. We are going to read the ADC with a function that returns a uint16 underscore t. And we're just going to call that read. And then we have to tell it the channel that we want to read. So a uint8. And then we need to tell it what our timeout's going to be. So we add another uint16 and we say it's the timeout equals to a default value of 1 second, so 100 milliseconds. So how do I know this? We go to our hull.h, we just scroll down again. So this is the file, and then eventually we will find these functions. We have our ADC start, which starts a conversion. Our ADC stop, which stops a conversion. We have a poll for conversion, which tells us when a conversion is done. Let's just check what that returns. Then we have poll for event, which polls for an event. And then we have ADC get value. If we look at that, get a regular conversion group unit, reading DR automatically clears the flags. Not much of a description, but this is what you use to get the ADC value. Now note this is a 12-bit ADC, so we only need a uint16 to return. So that's all the functions we require. And then we're going to copy our read function and start to implement that. Then we forgot to add this, and then we need to add this. So we add a uint16 here, and we say value equals to 0, and we create a hull status def here, we call it red for return, and that will be equals to hull underscore okay. And the first thing we want to do is we want to set the ADC channel. That's going to be return or return value. And we say pass in the channel that we want. Then we say if red not equals hull okay, then we return value. Then we have a look at our function definitions. Then we go to our ADC start so that we can start a conversion. And that will be our ADC handle, which is this private variable. So we've started the conversion now. Now we need to poll for the conversion. We can take away our default value over here. Poll for our ADC handle. And we give it the timeout. And then we say our value is equals to ADC hull get value, and then we need to stop the conversion, and that takes our handle as well, and all of these are going to be equivalent to red, and we just return the result if there's a failure. Actually, we can't return this. Okay, so due to this returning a uint16 and all we care about is the value, if we're not okay, we return the value that we got here. Usually it will return 0. So if something broke, step and debug it. That's the best I got. I believe that's everything implemented. Let's save this and build it. See what's the problem. ADC hull get value is not cleared here. Oh, I forgot to pass in the handle. Paste that. Let me just quickly build it. Okay, great stuff. It builds. So for our main program, so we need to initialize our ADC. We have our ADC base. Let's put this after the UART init. Then we just say ADC1, and our constructor is going to contain ADC1 as the instance, and then Control Shift Tab, and this is going to be our instance reference. So in effect, exactly the same as the UART. So our ADC1, since we're using 3 channels, we are going to add 3 channels. And we just copy this over. Okay, then we need to add our channels. So I need to look for that again. See our ADC init. So it's going to be ADC channel 0, 1, 2. And then we see our configurations here, and then just underneath it our sample times. We are going to max out the sample time again. I'm going to remove this print. We might as well start the read on the UART, but we're not going to be using it. So we're going to do a bit of a modification here. So this is going to be deleted. We say this is C0 for channel 0. So channel 0, 1, 2, 3. And that's going to be equals to ADC1.read channel 0. So we basically remap the channels to the vector over here. So the 0th index is going to be channel 0 and so on and so forth. And then read 1, read 2. Now, if we did not do this set channel and add channel and the read on a specific channel, we will just be reading on whatever the last ADC channel that was initialized. So you have to swap the ADC channels. We're going to add a print buffer for us. And we're just going to call it ADC buffer, which will just hold a printout for us. We get a memset to clear that buffer, and then we also clear it over here just for safety's sake. Now I've pre-prepped printouts for us. So this is going to be our first printout. It's going to be an SN_printf. So we limit the size that we can print. So it's going to be ADC1 and then the hexadecimal value for each channel, which I'm going to replace with C channels. And then we're going to do a UART print. So we're just going to print out the value on the UART and then have a 10 millisecond delay, and then we're going to print again. Okay, so we build. UART get TX is done. URDMA has no member got TX is done. Is TX done? Okay, let's go see what the issue is here. A declaration, URDMA. Let me have a look at the right. Oh, I did a small improvement for my code. So STM32 was not defined in the scope. Hash include std_lib.h if I remember correctly. And then we also need to include our ADC hull. So hash include ADC hull.h. Let's try to build now. SN_printf was not declared in the scope. Is it contained in the IO_lib? Huh. Okay, it's in the std IO_lib is SN_printf. That's interesting. Okay, so now that we build, now we can flash the chip. Okay, so the channels will be dependent, but you can see here, if I make a adjustment on one of the pots, you can see the first value changes, 0 all the way to 4,000 and something. That's 3,000, looks like it. And then we can go on the middle channel, and we can go, apparently the last channel doesn't want to work. Okay, let me just see what's going on here. So this one's 0. So somehow I'm piping the same value to both ADC values. Let me just have a debug session over here. Okay, let's see what's going on here. We have ADC1 read channel 1. This is channel 1, channel 2, channel 3. That's correct. Okay, print the buffer, the ADC buffer, C1, C2, C3. Okay, so let's start debugging. So we run to that. We step into our channel variable is 1. Step over, step into. I see what channels are. That doesn't help me much. Okay, there's the restart. Did I incorrectly configure this chip? Let's see. Because somehow channel 1 and channel 2 are linked, or channel 0 and channel 1 are linked. PIO settings. Looks to be correct. I'll be back after I debug this. Okay, so for interest sake in debugging, if you watch the value up there on the left hand side, and I restart chip. I click resume. Now I've got a breakpoint here before I do the readings. If you run it once, you can see all three have different values. If I run it a second time, values don't exactly match, but it's within range. And then when you start running it repeatedly, the two outer values, these ones, turn into the same value, which is not correct. So I'm trying to figure out the why on that. I'll be back when I got an answer. Okay, so I finally figured out the issue. In the ADC MX ADC1 init function, we just need to change the number of conversions from 3 to 1. And then we just leave the rest the same, and then everything works hunky-dory. So let's go to the camera. Now, as you can see on the top, I believe it's left. Let's see if I adjust one of the outer pots, you'll see the first value go up and down. So this is your raw ADC reading. So you can see it only goes to like 3,900 on this particular one. Then we have the middle one that's adjusted. Up and down, minimum 0, and then again 3,900. You can fix it with calibration if you really want to, but I'm not going to be covering that. Final one is being pain in the ass. Let's see here. What happens if I comment all of this out? So just so you guys can see, I've commented out all the channel initialization. Let's see if that makes a difference. Okay. Seems to be still stuck at the same value. Oh, it's on the last value. I'm blind as a bat. Okay, so if I adjust the last pot, you can see the last value go up and down. I'm just going to do a sanity check in the code. Let's see, it was ADC C. Control Z that. We flash again. Just check if that has no effect. Let's see the last value. Yeah, the last value works. And the last value works. You can see it go up, down. The middle one works. You can see that going up, down. Finally, the first value. So this one is the last value. This is the middle value. And that's the first value. All right. Now we can display it on the LEDs. So we go to our C main. Now this is a 12-bit value that we need to convert to a 8-bit value. So we are going to get our calculator. So 12 bits minus 8. So we need to shift by 4. And I'm just going to double check that. So 4095. So that's our 12-bit value. Yes. And if we right shift it by 4, we get 255, which is our LEDs. So it's going to be LED 1 to LED 8. So we're going to take channel 0 and map that to the LEDs. This is going to be a U8_D LED. I did not repeat the LEDs. Yeah. LEDs ADC. That's going to be equals to Z0. Right shifted by 4. I might have this the incorrect way around, but I do not care. So we take our LED bus. We say for I equals 0, I less than I plus plus. It's going to be LED bus dot size, LED bus index number, and that's going to be our LEDs ADC. Right shifted by I, ended with 1, so that we only have 1 bit there. Did I even create operators for this? I don't remember. Nope. We are going to write the value, and we're going to take this there, and we're going to cast it as a GPIO pin state. This whole thing needs to be inverted, I believe. Let's see what happens. Okay, so we invert the LEDs ADC, then we shift it by I amount. I amount gets ended with 1. And the brace there. Let's see what happens when I flash the chip. I have an idea I did this very incorrectly. So that's completely off. And apparently I did not do it completely wrong. That still does not look correct. Let's open a debug session then. Okay, we set a breakpoint over here. We quickly debug this. We switch to the debug perspective. Remove that breakpoint and we just quickly run to here. Okay, so LED ADC. Let's see what its binary value is. 111.011.00. Okay, so we resume. So this is the value we expect. A 111. We don't have a 111. 0. We have a 11 and then a 0. I'm suspecting that one LED is dead. I'm going to pause the recording and just double check the LED. Now, as you can see, the LED is on. It was just a loose connection. So we have the correct value here. Let's switch back to our code. Then we need to change the value. So we physically just change the pot. And we allow it to run again. So C0 is 275. Our lead ADC is 107, and that should be 10101010. Run the LEDs again. Camera 10101010. Okay, so that's functioning correctly. Fantastic. Okay, so finally we are going to display the ADC in millivolts. So we go back to the code. So I'm going to be creating 3 variables here. V1, V2, V3 as floats. And then we're going to do the conversion of the floats. I have already prepared this. Place those with C1. Okay, so since it's a 12-bit value, our maximum is 4096 steps. I am assuming our reference voltage is 3.3 since we're using the internal reference, and then we're just multiplying it by 1000 so that we can display it in millivolts. You have to enable a special flag to enable prints. Actually, I should stop debugging, and to be honest, it's not worth the performance penalty to enable the prints, but you can find it here in properties folder. I think it was settings. Here it is. So you get your project settings, you go to settings, you go to MCU settings, and use floats with printf, with new libnano -u printf, and you can use scanf as well. This is the one you want to tick or untick, but it's not worth the penalty. You just multiply your values by 1000 and you get what you need. Then we have a secondary print here, and then we just comment out the previous SN_printf. So this will now print the first voltage, second voltage, third voltage of channel 0123. So we just flash the chip. Now note it's displaying in millivolts again. Then we go and adjust the pots again. So the first channel around 3 volts if the connection is good. 3000 millivolts if you want to. Then we have 0. Okay. Then we have the middle channel. Adjust it all the way down. And adjust it all the way up to 3 it actually reaches 3.1 volts on that channel. And then our third channel, 3.2 volts, 0 volts. This is actually a more stable connection, looks like it. Yeah, that's the voltage. And then we can go disco on this, and we minimize it out. Alright, so that's an introduction to using the base ADC conversions on an STM32. A like, share, comment and subscribe is always appreciated. Thank you. Have a nice day.